At 02:43 on May 24, 2025, 3 Ukrainian attack drones sliced through the darkness over occupied Zaporizhia, zeroing in on one of Russia's critical supply lines. Along the Verkhniy Tokmak Molochansk railway, an 8-car train carrying roughly 616 tons of fuel, enough to sustain 2 Russian battalions for a week, rolled forward. The diesel was stockpiled to keep T-90 tanks and BMP-3 armored vehicles operational in southern Ukraine's offensives. Russian forces had no idea that within 60 seconds, this fuel would erupt into flames across the Ukrainian countryside instead of powering their tanks. That morning's operation unfolded with precision, involving 5 drones in a coordinated strike. A DJI Mavic 3 reconnaissance drone handled surveillance and target acquisition from 5 miles away. 3 Ukrainian-built FPV quadcopters executed the direct attacks. A second DJI Mavic stood by as a backup, ready to step in if the primary Mavic failed. Launched from a covert base near Melitopol, the drones were prepped and tested by Ukrainian engineers over the prior 48 hours. The pre-dawn timing leveraged darkness to minimize detection by Russian observation posts, which rely heavily on daytime optical systems. These drones were far from off-the-shelf commercial models. Ukraine's modified DJI Mavic 3 reconnaissance platforms were field upgraded with specialized specs. The stock Hasselblad L2D20C camera, boasting a 20-megapixel sensor and up to 28x hybrid zoom, saw some test versions enhanced with software for 56x digital zoom. Certain units were fitted with FLIR-Boson thermal cores for nighttime heat detection. These drones cruised at 42 miles per hour, with a 46-minute flight time and a maximum altitude of 19,685 feet above sea level. In contrast, Ukraine's custom FPV quadcopter attack drones were optimized for one-way missions. Equipped with 7-inch propellers on 2807 brushless motors, each generating up to 5.5 pounds of thrust, they were tuned with F7 flight controllers running custom Bellaflight software. These drones hit speeds over 87 miles per hour in their final dive, maintaining stability even during high-speed impacts, making them one of the most cost-effective attack solutions in modern warfare. From a secure command center 18.6 miles away, Ukrainian drone operators monitored thermal feeds as a distinct heat signature emerged against the cold backdrop. The DJI Mavic 3's thermal sensor detected temperature differences as small as 0.09 degrees Fahrenheit from 656 feet away. Upgraded software allowed the platform to evade Russian aeroscope detection systems, which track unencrypted DJI drone signals. The lead reconnaissance operator confirmed the fuel train's position via encrypted comms. The diesel locomotive's 1,200 horsepower engine produced a bright thermal signature against the night, simplifying target identification in total darkness. The locomotive's heat contrasted sharply with the cooler fuel cars, enabling precise targeting. Real-time reconnaissance footage streamed to attack operators in the command bunker. 3 FPV attack operators confirmed target data receipt through encrypted channels. Each Ukrainian-built one-way quadcopter carried a 5.7-pound shaped charge warhead designed for single-use strikes. These warheads, with dual-stage detonation and hardened tungsten steel alloy, could penetrate 0.87 inches of reinforced steel, exceeding the 0.39 to 0.59 inch thickness of standard Russian fuel cars. The shaped charges focused explosive energy into jets traveling over 30,000 feet per second, instantly breaching the fuel cars and igniting the contents at temperatures exceeding 4,500 degrees Fahrenheit. Ukrainian intelligence had tracked the fuel train for 72 hours using a network of guerrilla scouts equipped with basic smartphones. They mapped refueling schedules, an average speed of 25 miles per hour through the area, and a critical 15-minute window when the train was farthest from Russian Tor M2 and Panzer S1 air defenses, stationed 12.4 miles away. These civilian scouts, living under occupation and risking their lives, provided targeting data for such precision strikes. With the target verified visually and electronically, the lead attack operator initiated the strike sequence, guiding a Ukrainian-built quadcopter toward the moving train at a shallow angle. The drone's targeting system combined GPS with optical guidance in the final phase for maximum accuracy. During approach, encrypted GPS signals provided navigation. In the last 15 seconds before impact, the system switched to optical guidance using advanced image recognition algorithms. This dual approach optimized mission success. The Mavic ensured continuous surveillance and target designation from a safe distance, while attack drones delivered precise strikes with minimal delay. Hitting a moving train, however, was far more complex than it appeared. The train moved at roughly 36 feet per second, demanding flawless calculations. The attack drone's fixed camera, with digital stabilization, relayed real-time video to the pilot's goggles, maintaining visual lock even during final maneuvers. The 1080p camera, with a 90-degree field of view, allowed the pilot to adjust the drone's trajectory in real time, despite the train's sway on the tracks. The Russian fuel train remained oblivious that in just 30 seconds, it would become a massive fireball. At 0244, as the first attack drone entered its final dive, an unexpected issue arose. 3 miles away, a Russian Lear-3 electronic warfare system activated, detecting the drone's signal. Mounted on a KAMAZ truck, the Lear-3 carried jammers capable of disrupting GPS and drone control frequencies within an 18.6-mile radius. Its high-powered directional antennas swept the 2.4 GHz and 5.8 GHz bands, commonly used by commercial drones. The system picked up the drone's commercial signature and began broadcasting powerful jamming signals across multiple bands, attempting to force the drones to crash or return to base, exposing their launch site to Russian artillery. The drone operator reported heavy interference on the primary frequency as the control interface flashed connection warnings. Russian Lear-3 operators first deployed broadband jamming, blasting high-power noise across multiple bands. When that failed, they switched to spot jamming, focusing intense interference on the 2.4 GHz band. The Lear-3's 50-kilowatt output could disrupt drone communications under normal conditions. Ukrainian operators, however, were prepared. Their system used frequency-hopping spread spectrum technology, switching frequencies hundreds of times per second across multiple bands. Operating on 2.4 GHz, 5.8 GHz, and a backup L-band, it changed frequencies up to 1,200 times per second. This rapid switching made it nearly impossible for Russian jammers to lock on. Both the DJI Mavic reconnaissance platform and attack drones employed this technology across 3 bands simultaneously, a setup designed for contested electromagnetic environments. The Mavic continued delivering real-time intelligence, automatically scanning and switching to alternate frequencies when jammed. The Mavic's AI-enhanced sensors maintained target tracking even when attack drone communications faltered. The operator reported switching to a secondary frequency as the attack system hopped to a backup L-band channel. The primary data link distributed signals across multiple frequencies, changing patterns up to 1,200 times per second, rendering Russian jamming ineffective. The Mavic 3's AI, trained on Russian railway imagery, ensured continuous tracking despite heavy interference. Russian Lear 3 operators escalated their efforts, attempting GPS spoofing by broadcasting fake satellite signals to mislead the drone's navigation. Ukrainian drones' inertial measurement units detected discrepancies between GPS data and actual movement, automatically switching to backup navigation. Accelerometers and gyroscopes within the drone's navigation computers tracked velocity and direction changes with 0.01 degree per second precision, providing jam-proof navigation. The operator reported GPS signal degradation, but switched to inertial navigation as the attack drone closed in on the train despite electronic interference. The targeting system locked onto the fuel car's structural features, using image recognition to maintain accuracy even as the train swayed. The attack drone's computer, loaded with algorithms trained on Russian railway equipment, identified fuel cars despite smoke and thermal distortion. Even without continuous operator input, the system could identify fuel cars, calculate optimal impact points, and execute the final strike autonomously. The operator reported activating autonomous mode as the drone entered its terminal phase. Despite Russian electronic warfare disrupting one channel, they couldn't stop what followed. At exactly 02:44:30, the Ukrainian attack drone slammed into the third fuel car with devastating effect. The 5.7-pound shaped charge warhead detonated on contact, its tungsten steel penetrator piercing the car's 0.47-inch steel wall before the secondary charge ignited the high-pressure diesel inside. The explosion tore through the car at over 4,500 degrees Fahrenheit, vaporizing hundreds of gallons of diesel and generating a massive pressure wave that shattered the car's structure. The attack operator confirmed a direct hit on Car 3 as the thermal camera on the Mavic showed the explosion's heat signature spreading rapidly. The target was engulfed, with secondary explosions erupting as the destruction spread to adjacent cars. These secondary blasts, triggered by vaporized fuel in the cars, produced fireballs up to 98 feet in diameter, shaking the ground within a 1,640-foot radius. The fuel train's design, optimized for efficient transport, became its downfall in combat. Interconnected ventilation systems between adjacent fuel cars, used to balance pressure during refueling, now channeled the flames. Within 15 seconds of the first strike, flames from the third car ignited fuel vapor in the second and fourth cars. The Russian locomotive engineer activated the emergency brake, applying 1,200 kilonewtons of stopping force, halting the train abruptly and turning it into a stationary target for the remaining drones. Now motionless, the train was easy prey as the next two drones dove in for the kill. At 02:45, with the initial target engulfed in flames, the second and third attack operators launched coordinated strikes. The burning train was a sitting duck. The second operator targeted the sixth fuel car, still intact despite the spreading flames. The Ukrainian quadcopter approached from the southeast, using smoke and fire as cover, while its thermal imaging locked on to the cooler metal signature of the undamaged car. Flying at 164 feet, it used thick smoke to evade Russian ground observers. The targeting computer compensated for thermal distortion from the burning cars, ensuring precise navigation despite worsening visibility. The DJI Mavic continued providing surveillance and target designation, its AI-enhanced sensors automatically identifying and prioritizing intact targets. The platform's advanced thermal imaging cut through smoke and flames for a clear view of the target area. The operator reported engaging Car 6 as his drone entered its final dive. The shaped charge warhead struck with the same precision, piercing the car and igniting another 76 tons of diesel. The explosion merged with the existing blaze, creating a fire spanning 4 consecutive cars. Simultaneously, the third operator targeted the train's rear, where 2 fuel cars remained untouched by the spreading flames. Approaching from the west, his drone struck the 8th and final car. Using a low 10-degree approach angle to avoid debris from prior explosions, the impact triggered the same destructive sequence: penetration, ignition, and catastrophic fuel combustion, adding another massive fireball to the inferno. 3 precise strikes had now ignited roughly 616 tons of fuel, creating a blaze that generated its own weather system. The fire's core reached 5,400 degrees F, producing powerful convective currents that sucked in air at 31 miles per hour, pushing smoke and flames over 656 feet into the night sky. The railway itself was rendered unusable. Intense heat warped the tracks into twisted metal, wooden ties burned to ash, and debris from the exploded fuel cars littered the area. Russian repair crews would need weeks to restore the line, assuming they could work without facing further Ukrainian attacks. The loss of the fuel train severely disrupted Russia's supply chain, forcing them to divert resources from fronts like Donetsk or Kherson. Estimates suggest the 2 Russian battalions reliant on this fuel will pause offensive operations for at least 10 days, giving Ukraine a window to reinforce its defenses. The attack not only destroyed a key logistical asset, but also sent a powerful message about Ukraine's ability to execute precise operations in complex battlefield conditions. The integration of guerrilla reconnaissance, advanced drone technology, and countermeasures against Russian electronic warfare turned a fuel train into a symbol of Ukraine's resilient resistance. Data from similar strikes indicates Russia has lost at least 12 such fuel trains in the past 6 months, significantly weakening their logistical capacity in occupied territories. That's all for now. We hope today's report provided valuable insights. If you found it informative, please give it a thumbs up and subscribe for more compelling content. Drop your thoughts in the comments below. Thanks for tuning in, and we'll see you at the same time tomorrow.